So I will present also on behalf of my co-authors in the framework of this cooperation we are having with Isfahan University, which was mainly mediated by the first author, Mehdi Khorasani, who spent a significant part of his PhD in Milan. Mehdi could not make his way through here, and so I am presenting on behalf of everybody. So as per introduction, I mean, my main focus actually typically is on innovative materials, innovative cementitious materials, and anchorage fastening. So I'm a little bit a guest in FRP context, and I will try to mainly explain why, what we are trying to do with the colleagues. So I will skip this. Okay, and let's start from this. Let's considering something a little bit more general. And by the way, sorry for the format. I realized during the presentation from this morning that there was something not working with format we tried to use in the ACI format. Anyway, so it is a little bit different than others. So when one of the issues we know very well, and when we are passing from, let's say, the specimen that we typically make in the lab to on the left, which was the right specimen, what we have real structure, we have some boundaries, we have some geometrical boundaries, which force us to some extent to use some specific solutions to guarantee, the effectiveness of the strengthening. One of them, for instance, is the CFRP anchor, on which a lot of this cooperation which we started is working, which we are also starting to investigate through experimental techniques and analytical methods, which are more typical of fastening technique, which what you see on the right. And in this field, for instance, we obtained some results which I would like to quickly show here. So, for instance, we start to investigate which is the sensitivity to installation, so guarding against how you clean and which can be the effect of the sensitivity technique. Capacity prediction, which is in the middle, through models which are more typical of fastening. So, for instance, prediction regarding models which look at concrete capacity, or the bond through models which can be applied to different conditions which you may have, and this seems to work pretty well. Or even also the behavior under temperature, evaluating the decay, for instance, bond strength through techniques which are, say, borrowed to other worlds. So this is a little bit to give you the idea, okay? Even if I will not focus specifically on FRP anchors today, as you may see from the presentation, but to another technique, which may be used when we have some geometrical boundaries, which was maybe developed by the colleagues in the past, which you may know, I can skip this, when you basically have some issues, in the anchorage, so you may want to use some grooving methods. So grooves basically are here, no? So assuming that this will not, okay. So, well, you know very well, okay, all the basic preparation which you may have in the standard case, and also, say, some techniques which are coming through the last year, so near surface mounted under things. And the grooving basically consists in wanting to have some mechanical interlock which may help us a little bit. So, we cut through, okay, the concrete, and then we let the resin go in. Of course, this may be coupled with other things which are under evaluation today. So, having in the groove not only the resin or the matrix, but also, let's say, to have the strip which can go through the matrix. Anyway, these are coming. Let's put it like that. I will focus a little bit today on this specific technique in one specific condition, which is the assessment of the fatigue behavior, or specifically of the resistance in this case, as we'll see. So, what I will talk about in the next minutes is the evaluation of the efficiency of the EBROG method on bond properties of FRP composites under fatigue loading. Try to see if this can be predicted, okay, somehow, and show some possibility. The evaluation of the effect of different groove dimensions on the performance of the joints, and let's say a little bit, the effect of the loading amplitude also on the fatigue life of bonded joints. So, to the scope, we casted some specimen in our lab, so we casted our slabs, some slab. The concrete class is the basic one. This is the bonding material, the fiber adhesive that we use, not because we had some specific agreement with the manufacturer, just because it was available on the market, so we're also promoting somehow this, but it's not, it's just indirect. So the methodology of preparation. So this is the procedure we follow for the standard method, so the standard bonded reinforcement. So we remove the weak layer, weak thin layer of concrete, then we apply the epoxy-based adhesive, and then the sheets after impregnation, okay, as known. And just want to stress, which is the only difference which we have in the EBROG method, which before doing the rest, you cut the concrete. So this was done by through lab tools, okay, which are actually can be easily available also on the job sites, and then you cut through the concrete, you clean, okay, actually this seems trivial, but it's not, you clean, here we see some brushes, and then you proceed, okay, with putting the resin, and then we're going on with the impregnated FRP sheet. Now, there are these typically awful tables in presentation which are taken by paper, which are impossible to understand. I want just to focus on one thing here. So this we find, of course, the details in the paper if you're interested. Just one thing, that we tested external bonded reinforcement, okay, and with grooves, and we just check monotonic behavior, fatigue behavior, varying what? Varying the size of the grooves, okay, the width and the length, and varying the numbers of the grooves. So these are the parameters which we checked, which compose in the end this test layout, and then for each specific combination you find all the details in the paper. This is the test setup that we have in Milan. This was mainly developed by other colleagues in the past, and we are basically pulling parallel to this surface, and the specimen here is locked to the floor, okay, of course, because we have the bending which is induced in the specimen. The only thing I want to stress is that we have some vertical supports here, and we have also put a camera for data acquisition to process a little bit through the DIC. Comparing the results, I can show you in this, which is shows better. Comparing also the result of DSC with some more classical measurement, for instance, through some LVDT. So here you have some side view and the top view. The details are basically the one which I explained. As for fatigue, in particular, now what we can see is that while the video runs, okay, so while you are video returning through the cycle, what we check is several things. Of course, we check this. Okay, let's say not inverse loading, it was not the scope, and we basically cycled through different load levels without complete unloading, also because this would not correspond to a real situation, investigating a little bit the effect of the amplitude. In the end, I will focus mainly on the maximum load which was achieved, but it was also to show that we also will keep always a minimum load. The frequency was decent, also with respect to the number of cycles that in the end we achieved. Before looking at the results, I think it may make sense to look a little bit more at the failure mode, because here something interesting comes out. So here you see the failure after monotonic testing and after fatigue testing, and it's interesting to see that there is a transition in failure mode somehow. Okay, so it's more evident in the standard installation that we have grooves, but you basically see that the failures moves failure surface from, let's say, to the adhesive to concrete interface to within the adhesive. Okay, this is very evident in the in absence of grooves, but also like a little bit, as you can see, even when we have grooves, when you see basically the surface is more clean. That was an interesting presentation early in the morning regarding how we can quantify also, okay, the parts of adhesive and concrete at failure through evaluation images, and I think this also can be taken here. Then, as also reported in the past, grooving allows for the same length Yeah, we are talking about, it was a picture before, but the strips were 35 millimeters and were anchored 20 centimeters, okay? And here you can see, if you just look at the total capacity, that we may have with grooves an increase in capacity, okay? But this could be expected. This is one of the processing which we have from the images, which shows the strain distribution. And when you add the bonding initiation, okay, here 0 is where we have the starting of the bonding length, as also per standard, and also shown also in another presentation. There is the initial part, of course, which is unbonded, and this is not shown. So you are just showing the strain distribution along the bonded length, which is 20 centimeters. Here you can see that external bonded reinforcement, okay, it's initiation and then also a final stage. This is quite spread, while when you have groove, of course, I mean, you are reducing the transfer length, so you are concentrating more in the initial part. The latest part, I would say, it's quite ineffective, so I can skip this because it just says the same thing that you were saying before. And I think we can use these 2 minutes to focus on this. Okay, so this is, again, one of these awful tables with results which are not clear, but let's see what we can extract from this. So let's start from the standard. So in absence of growth, we cycle between 2 load levels, so 20% of the mean capacity and 65%, which gives us some specific load levels in terms of load values with a given number of cycles at failure. So if we keep the same load level, okay, so we keep the same maximum, for instance, 65% of the minimum ultimate capacity, but with growth, the number of cycles that we can get is lower, of course, because this corresponds to a higher load level. But if we keep, for instance, the same load values, so absolute values, which were detected in the initial case to the case with grooves, which is what you can see here, then the number of cycles dramatically increased. So we got 1 order of magnitude more. And this is the result I would bring home, okay, as for now. Just to say, and then I concluded, as to say that this can be very effective if, for instance, we want to just count, okay, so there's additional mechanical interlock, in case we can have maybe also the same transfer length, but we want to increase, okay, the fatigue life. This is just a graph which reports as a function of the load level and the number of cycles, which is typical, no? Relationship between these 2 parameters, and this is just a purely brutal predictive equation which shows, okay, how this can decrease. We try to apply models which are existing in literature, not developed for grooves, and they don't work, of course, so we had to develop some models, but just to show that at least from a semi-qualitative point of view, this can be predicted. So I should be in time. So just these 3 main conclusions are that we can have a significant increase in the number of cycles by using the EBROG method compared to the EBR method at the same loading levels. This is important. Load amplitudes, as well known, to affect the fatigue life of bonded system, while reducing the maximum applied load increases the fatigue life, the strength of the joints, and just proposing for the moment a predictive equation based on the maximum applied fatigue load for this type of installation method. Maybe the first author asked me to show this picture of the guy in the lab with a technician. When I showed this, I realized that I do not go so often to the lab anymore as in the past, because I'm not anymore in this kind of picture at the end of testing. Anyway, thanks to everybody for